Radial basis function, and in that we are going to cover the aspects of separability and interpolation. Now, before we go into this aspect, we need to quickly summarize what we did in our last lecture. Now, in the last lecture, we had introduced the radial basis function, and where few of the points which you should notice that firstly that it is a multilayered perceptron, but here the problem is formulated in an interpolation way, not in a stochastic approximation way. That is number one. And then we had seen a very important theorem, which is Covert's theorem, which states that if you are mapping from an input space to a higher dimensional hidden space, then its separability increases. So, we had presented the mathematical expression which shows us that. Okay. That means to say that where we consider that the patterns are separable, in the input space the patterns are separable, but not in the linear separability. They don't have the linear separability, but when we map it into the phi space or the hidden space, then it is becoming linearly separable. So, in other words, with respect to the input space, we are having a kind of a nonlinear separability, which we had shown one or two examples that it could be a spherical hypersphere separability or any quadric separability. All these things can exist. Now, the two basic important points that came out of Covert's theorem is, number one, that the mapping that we are doing from the input space to the hidden space, that is essentially nonlinear. So, one of the basic fundamental things that we have observed is a nonlinear mapping. It is a nonlinear mapping from input to the hidden space. Okay. That is number one, and number two is a higher dimensional mapping. In other words, we must ensure that when we are mapping from the input space to the hidden space, then preferably phi should be having a higher dimension. In fact, with increase of dimension in the phi space, the possibility of having a linear separability in phi space increases. In fact, we can very easily guess that what would be the structure of such a kind of an RBF network, because what happens that we are first taking the set of inputs, those inputs we are mapping into the hidden space, and that mapping is being done by a set of basis functions. Now, all these hidden neurons that we are taking, they are working based on those functions. Okay. And then these functions are, so then these mapped values, okay, which is in the M1 dimensional of real space, if we are taking M1 to be the number of hidden neurons, then from the hidden neurons to the output, okay, there we can keep the usual linear activation unit neurons, because once we have separated out the patterns, okay, in the once we have performed a linear separability after mapping into the phi space, there is no other difficulty for us to remap it into remap it into the output space using the neurons. Okay. So, that is there, and now these 2 points that we have got out of Covert's theorem, that is nonlinear mapping and higher dimensional mapping. In this, the essential that is there is the nonlinear mapping. Okay. Higher dimensional mapping is indeed preferable, okay. But of course, that increases the cost, because if you are keeping too many hidden neurons, okay, as used as the radial basis function, okay, then you are increasing the cost of the system. Now, even if you do not decide to increase the number of hidden neurons, okay, if supposing you try to keep the dimensionality of the input space and the dimensionality of the hidden space to be the same, okay, then the essential point that one must have is that there should be a nonlinear mapping. Now, nonlinear mapping is very essential, even if you keep the dimensions same, okay. If you are performing a proper nonlinear mapping, okay, in that case it is possible to have a separation. Now, what we are going to now in yesterday's class, what we were actually talking about was that when we are mapping from the input space to the hidden space, then we have to use some basis function, and now we are going to show that with one simple example. And again, the simplest of the examples that one can always think of regarding the linear separability is our very popular exclusive OR problem. So, we are going to take up an exclusive OR problem and a very typical example of the radial basis function, which we are going to take from the book by Hakins. So, Hakins neural network book itself gives this same example, and which I am going to tell you for your better understanding. Now, let us take, so this is an example of XOR problem, and what we have here is that let us first draw the input space, right. So, we draw the input space. So, the input space is the X vector space, and the simple exclusive, the simplest of exclusive OR is a 2 input exclusive OR, where we are having 2 inputs and 1 output. So, the X vectors components are X1 and X2, which we are showing in the form of these 2 axes. Now, that means to say that the patterns that one can feed to this system are 0 0, okay, 0 1, supposing this is corresponding to X1 equal to 1, and then 1 0 and 1 1, these 4. Now, out of this actually 2 patterns, they belong excuse me, out of these 2 patterns belong to the class 0, okay. Let us say that okay, 0 0 means that it is okay. This belongs to class 1, and the open circle that we have drawn, that belongs to class 0, all right. So, now what we are going to have is that we are going to okay. So, it is definitely not linearly separable in the input space, okay. So, what we do is that we use a pair of Gaussian hidden functions as the radial basis function. So, as radial basis function, we take a Gaussian function, or rather 2 Gaussian functions are used as basis. One is phi 1. So, where the definition of this basis function is phi 1, whose argument is the x vector, is equal to e to the power minus norm of x vector minus another vector, which is a T1 vector, having of course the same dimension as that of the x vector. That means to say that here x vector's dimensionality in this example is 2, because there are 2 inputs over here, and likewise the T1's dimensionality will also be 2, and this is and this norm should be taken in the square. So, that means to say that this is our very popular Gaussian function, which you can immediately identify. Now, this T1 basically is what? T1 is nothing but the center of the function. I mean, so the Gaussian function that we are considering is definitely centered around T1, okay. So, this T1 we can take some of the, so T1 we take centered around two of the patterns that is giving us a class equal to 0, let us say. So, we take this and this to be the centers of the Gaussian. So, we take T1 vector to be equal to 1 1, and we likewise take another radial basis function phi to x, which is equal to e to the power minus x minus T2 this square, and T2 in this case is defined to be the 0 0. Okay. So, these are the two centers around which we have defined the radial basis function. So, how many radial basis function we consider? Only 2. Our dimensionality is also 2. That means to say that when we are remapping the function from the input space to the hidden space or the phi space, we are not changing the dimensionality of it. The dimensionality still remains as 2. All right. Now, what we have to compute is that now phi 1 x and phi 2 x, there are two radial basis functions, and we have to compute their values, the values of these functions, because ultimately these functions are going to give us values in the real space, isn't it? And if we consider the values of phi 1 x and phi 2 x together, then that gets mapped into a two-dimensional real space, R square space it gets mapped to. So, then what we have to do is that we have to yes. So, let us now start mapping it. That means to say that for x we have to substitute the various values, like 0 0 could be the 1, I mean let us take phi 1 x. So, once we will compute phi 1 x with 0 0 pattern, then we will be computing phi 1 x with 0 1 pattern, 1 0 pattern, 1 1 pattern, and like that phi 2 x also we will be computing for 0 0, 0 1, 1 1 and 1 0. Now, you can see that the values will definitely be different, like say for example, we can very clearly see that when x vector is fed as 1 1, then it becomes e to the power 0 over here. So, which means that the mapped value, mapped real value for the phi 1 function becomes equal to 1. So, let us see that what values do we get out of this. Okay. Now, the values that come out after the computation of this, so can be written as follows. So, for x vector, so we make it in a tabular form, the results of the phi 1 vector and the results of the phi 2 vector, all right. And when x vector is equal to 1 1, then phi 1 vector gives what? A value of? No, e to the power 0. E to the power 0 means the phi 1 value is equal to 1. Okay. So, this is equal to 1, and phi 2 will be a value of course other than 0, other than 1 it will be, because x vector then becomes equal to 1 1. No, I mean x vector becomes equal to 1 1 and T2 vector is 0 0. So, there will be some real value that is computed, and in fact, if one takes down a calculator, it is possible to calculate that phi 2 x is equal to 0.1353. Okay. Then we take 0 1. Now, 0 1 you see 0 1 is not any of these radial basis function, this Gaussian function centers. So, that means to say that both phi 1 and phi 2 will give some non-zero and non-1 real values. Okay. In fact, the values that work out to be, in fact, they are becoming equal values. So, the values that are computed are 0.3678 for phi 1 and 0.3678 for phi 2. And then for 0 0, what is it that one can expect? 1 for phi 2 definitely, because phi 2's center itself is 0 0. So, for phi 2 we will be getting a value equal to 1, and for phi 1 we will be getting the value that we had got out here, because I mean after all it is a squared norm that we are computing. So, I mean the value of this will be 0.1353, and what will be the value of 1 0? Any guess? The value, the same value that we had got for 0 1's case. So, that is 0.3678 and 0.3678, and now we plot. Now we plot in what space? Not in x1, x2 space anymore. Now we have to plot it in the phi 1, phi 2 space, because that is our mapped space. So, now we have phi 1 in this axis and we have phi 2 in this axis. So, this is phi 1 x and this is phi 2 x, and we plot these values. You see that now, I mean, if we are considering, I mean, let's take this to be 0.2, this to be 1. So, that all these divisions that I have marked are in steps of 0.2, and likewise here this is equal to 1. So, here all these are in steps of 0.2, right. So, we can see that when it is 0, 1 or 1 0, the values that are coming are I mean 0.36, 0.36, again for this one also 0.36, 0.36. That means to say that we will be having a point somewhere here, right. We will be having a point somewhere here where the phi 1 value and phi 2 value both are 0.36, and they will be corresponding to the pattern 0 1 as well as 1 0. Both the patterns will be mapped into the same position, all right. Now, these are what? These this should be open circles or closed circles according to our definitions. They should be closed circles. Okay. So, this is the 0 1 and 1 0 pattern, and then for 1 1 pattern, where will it be? It will be with phi 1 equal to a value of 1 and phi 2 equal to a value of 0.13. Okay. So, somewhere over here there will be an open circle, okay. And likewise for phi 2 equal to 1, phi 2 equal to 1 means here, and phi 1 equal to 0.13, we will be having another value, okay, with open circle. So, this will corresponding to phi 1 equal to 1 and phi 2 equal to 0.1353 would correspond to the pattern 1 1. Am I correct? Yeah. And this one will become phi 1 equal to 0.13 and phi 2 equal to 1, which will make it actually 0 0. So, now we see that this is the space, and now I can consider a separability by simply imagining a line like this. So, the pattern which was inseparable in the original x1 x2 space, inseparable means linearly inseparable, of course, okay, but they are now becoming separable in the phi space, okay. So, this is the example that shows us that it is simply by nonlinear mapping. What we have done is nothing but mapping from the x space to the phi x space. So, by simply doing this nonlinear mapping using Gaussian as a function, we could map it into a space where we could find a linear separability. So, that means to say that the function that we have designed is basically a, so in this problem we find that there is a phi separability. We were talking about a phi separability in the last class. So, phi separability is demonstrated by this example. And now, any questions pertaining to this? Okay. Now, we go over to the discussion on the separating capacity of a surface. Now, you see, after all, what happens is that finding a line, in this case it becomes a simple line, a linear separability. For 3 dimension it becomes a plane, for multi-dimension it becomes a hyperplane separability in the phi space. Now, the thing is that it essentially transforms to a nonlinear separability as far as the input space is concerned. Now, the question is that if you keep on increasing the number of patterns, let us say, okay, I mean you are feeding the patterns as x1, x2, x3, x4, I mean all this in the form of vectors, mind you. So, we have got an m0 dimensional input space, let us say. So, what we have is M0 dimensional input space. So, this is the input space dimension, and we take a sequence of random patterns, and those sequence of patterns are x1, x2, etc. up to xn. So, this is a sequence of random patterns. Now, we would like to know that if we keep on increasing this n, okay, then what is going to happen with the probability of separability. You remember that in the last class we were considering the probability of separability, and the probability of separability in the last class we studied from a different standpoint. There we were keeping the M1, that is to say the dimensionality of the hidden space. So, M1 is taken as the hidden space dimension. So, we there considered the dimensionality of, while proving Covert's theorem, we were taking the dimension, the hidden space dimensionality to be one of the variables, and then showed that as M1 increases, the probability of separation improves. But the thing is that if, let us say that we have decided our structure, that okay, we are going to have, freeze it, that we are going to have M1 as the hidden space dimension with us. Okay. Then the question is that from the M0 space, then the question is that how many such patterns can we have? Okay. If we increase n, okay, are we going to increase the are we going to improve the separability, or are we going to make the separability worse? So, what we are going to do is that we are going to take now n itself to be a random variable. So, now we define n as a, let n be a random variable, and how is n defined? This is defined to be the largest integer. So, this is defined as the largest integer such that this sequence is phi separable. Okay. So, how we are going to formulate the problem? We are going to take the probability that this capital N is equal to n. We just write down and then you will be able to know. Now, in the last class we had shown you the probability expression. So, you can keep that in your reference, and then one can work out that the probability that n is equal to n will be given by the probability n comma m1. What is n comma m1? N comma n1 means that there are n patterns, okay, which are getting mapped into m1 dimensional hidden space. Okay. This minus p of n plus 1 comma m, obviously which is going to be higher, p n m1 is going to be higher. Why? Because if you change from small n to small n plus 1, if you are increasing the patterns, then the separability probability is decreasing in the n. So, this in fact, if you are substituting the expressions that we had shown, okay, in the last class for p excuse me, for p n m1 and for p n plus 1 m1, then we can write down that this becomes equal to half to the power n and the combination n1 c m1 minus 1. Okay. And this we have to, this will be defined for n equal to 0, 1, 2, etc. Okay. So, this is the probability that we are getting, and this expression that we have got has got a negative binomial distribution. This distribution is a negative binomial distribution. In fact, the negative binomial distribution is the one that we are normally getting from the long repeated Bernoulli trials. Okay. So, what we have to consider is that, I mean, you can consider any binary event experiment, let us say tossing of a coin, that is what you take, and you take the probability, okay, that k failures, I mean in a coin tossing experiment, let us say you have k failures preceding rth success, and what is so that means to say that it is a long repeated binary trials. So, we are keep on repeating this trial. Now, there is a first success, then again some failures, then again the second success, again failures, then again the third success, like that it goes on. So, it is coming from a long repeated Bernoulli trial. In fact, those who are interested should refer to any good book on the probability and statistical theories, okay, where this will be definitely presented. So, what we have there is that, let us say that we define two probabilities P and Q. So, let P and Q be the probabilities of success and failure. So, necessarily what we are going to have is P plus Q should be equal to 1, and in this trial of experiments the binomial distribution, I mean the negative binomial distribution will be defined as follows. So, this will be defined as f of k, okay, r comma p. Okay. Now, this is k failures, rth success, and p is the probability of the success. So, this distribution is given by p to the power r, q to the power k, and a combination of r plus k minus 1 k. So, now if we take a very special case, so for the special case, like this is nothing unrealistic, I mean a fair coin toss. So, for a fair coin toss we are going to have P is equal to Q is equal to half, right. So, when we have P is equal to Q is equal to half, and as a special case we take that K plus R is equal to N, alright. We take K plus R equal to N, then what it comes to is f k r comma p is equal to half to the power n. You simply get that because you have p and q both to be equal to half. So, it is half to the power r plus k, and r plus k is equal to n. So, we get half to the power n, and here because r plus k is equal to n, we are getting a combination n minus 1 c k. Okay. And this we have to do for n equal to 0, 1, 2, etc. So, this expression is nothing but a negative binomial distribution. So, what we have got, okay, as the probability of n equal to n is a negative binomial distribution. Okay. So, what essentially it means that we are varying this n. Okay. We are, I mean, keeping this n as a random variable, and we are getting a very interesting distribution. We compute n equal to 0, 1, 2, 3 like that, okay, and we get some kind of a distributed, I mean some kind of a distribution pattern, okay, and n is considered to be a random variable. So, definitely I mean from that distribution that we get, it is possible for us to find out that what is the expectation of n, because that is very important. Expectation of n, if we can determine from this set of statistical experiments, then from that expectation of n we can decide that okay, if that expectation is expressible in terms of m1, where m1 is the dimensionality of the hidden neuron, then it is possible for us to say that okay, the maximum number of n that you should have is that the maximum number of patterns that you should feed should be equal to 1.5 times m or 2 times m or 2.5 times, and whatever it works out from the expectation. In fact, the expectation and the median of the random variable n works out to be 2 times m1. I mean, if we go through this mathematics, then we are getting the expectation of n. I mean, out of this distribution, out of this negative binomial distribution, we are getting the expectation of n to be equal to 2 times m1, and even the median of n is going to be 2 times m1. Okay. So, that means to say that we can definitely say that 2 times m1 is a natural capacity of separability. Right. So, in Covert's theorem we were considering separability from the standpoint of variation of m1, the very fact that we wanted to show that the higher dimensional space results in a better separability. Here we are calculating that fixing up m1, we are calculating that what is the capacity of separability in terms of its number of patterns, where 2 times m1 becomes a good number. Okay. Now, having done that, having known about the separability aspect, now we are in a position to begin the basic fundamental approach to the radial basis function. And again I repeat what I have been saying over the last 1 and 2 lectures, is that essentially for radial basis functions we are looking at it exclusively from an interpolation point of view. The whole problem is an interpolation problem, and let us in order to formulate that interpolation problem in a nice mathematical way, we define a feed forward network. So, we talk about the interpolation problem now, and there we take a feed forward network. So, we consider a feed forward network for which we are having input layer, a single hidden layer, and an output layer, and just for our ease of analysis and simplicity and without any loss of generality, we take that there is only one neuron in that output unit. So, there is so as the output layer we are having only a single unit. Okay. That is just for our simplicity that we are going to consider. So, essentially what this network is going to do is that from the input space, let us say this is the input space, okay, it is getting mapped non-linearly into the hidden space. So, this is a non-linear mapping from the input space to the hidden space, and then from the hidden space to the output space there is going to be a linear mapping. Okay. So, in output we will be just combining these outputs of phi's, phi 1, phi 2, phi 3, phi 4, whatever we get. Okay. Those real values we will be weighting up W1 phi 1, W2 phi 2, like that, and we will add it up, so that we will be generating a linear output. Okay. So, it is essentially a mapping from input to the hidden, hidden to the output. Combinedly looking at it, it is definitely a mapping from the input space to the output space, and combinedly it is of course a non-linear mapping, is not it. So, it results in a non-linear mapping from input to the output effectively. Okay. Now, the inputs dimensionality we are considering to be M0, the single layer, I mean I should have written single hidden layer. Okay. So, please note that it is a single hidden layer, and this hidden layer is having M1 number of neurons. So, its dimensionality is M1. So, what essentially means is that from the M0 dimensionality input space, we are mapping into the output, which is a single unit. That means to say that what is the output dimension? Output dimension is simply 1. So, essentially the mapping that we are considering for this network is, if we say that the mapping function is S, then S is a mapping that is defined from M0 dimensional real space to 1 dimensional real space. Okay, this is the input and this is the output. So, what is this S? I mean, what is the interpretation of this S? This S is a surface. This S is a surface. Surface of what dimension? Can anybody tell me? Surface of what dimension? M1? No, there is no M1. I mean, I have considered the entire mapping problem in an integrated way. I mean, input to output. I am not considering the in between mapping that we are doing to the hidden layer. Hidden layer has performed its job, and we are now looking at the whole radial basis function network from a black box point of view. There is input, there is output. So, there is no M1 that is coming in. It is a simple M0 dimensional to 1 dimensional mapping. Okay. In order for you to answer the problem, okay, in a better way, supposing we have got, I mean not here, supposing we have got some mapping function, okay, which maps from one dimensional space to another 1 dimensional space. So, let us consider a 1 dimensional to 1 dimensional mapping. Okay. You have got some real number and you are mapping it into another real number, that is it. So, I mean there is a mapping function that is available, okay, for those real numbers. I mean you are taking several real numbers, I mean several real numbers belonging to this space getting mapped into a set of real numbers in this space. Okay. So, definitely there is a function that is defined, and how are you expressing that function? That is also a surface fitting problem only, but in this case it is a curve fitting problem. 1 dimension to 1 dimensional mapping is essentially a curve fitting problem. Why? Let us take that this is the domain of this. Okay. So, this is the domain of this R, this function, and then this is the domain where it is getting mapped. Okay. So, this is our input and this is our output space. Okay. Now, this input to output is a mapping which is done by the definition of some curves. Okay. So, we are going to have some curve, maybe a curve like this which is there, and this curve is defined in which dimensional space? 2 dimensional space. So, 1 dimensional to 1 dimensional mapping, okay, results in a 2 dimensional surface. 2 dimensional surface of course degenerates to a curve. Okay. So, it is a 2 dimensional surface space where this S belongs to. Now, just complicate the problem a bit. You define that you have some inputs in the R2 space, 2 dimensional space, which you are mapping to another space which is R1 space. So, it is a 2 dimension at the input, 1 dimension at the output. So, how are you going to represent that problem? You are going to draw 3 axes like this, okay, where the original input space you will be showing with respect to this, and the mapped values that you are getting, that we will be showing in this axis, in the z axis, and for the input space we will be showing in x axis and y axis. So that the interpolation problem, so that the fitting problem that you have got there, the surface that you have obtained there is a 3-dimensional surface. So, R2 to R1 mapping, R1 to R1 mapping in a 2-dimensional surface, R2 to R1 mapping in 3-dimensional surface, make it R3, it will be 4-dimensional surface. So, make it M0, it becomes M0 plus 1-dimensional surface. So, that map S is now to be imagined. So, S is a hypersurface, and what is that hypersurface? It is the hypersurface gamma. Okay. So, we take the hypersurface gamma, okay, which belongs to the M0 plus 1-dimensional real space. Okay. So, what happens to us is that this surface, okay, this surface that we are having is unknown to us. Okay. And how are we going to know it? Through the training. Okay. We are going to feed the training patterns, okay, where essentially what we do is that where we definitely know, I mean feeding the training pattern means that where we know definitely the input output mapping. So, the mapping function is initially completely unknown to us, okay, and we are going to feed the training pattern where we know that, okay, we are telling them that, okay, this is the M0 dimensional point corresponding to which the output that you are getting is this, we are specifying that. So, that means to say that the surface which was unknown, for that we are feeding some of the specific points, but those specific discrete set of points does not constitute a surface, is not it? Does it look like a surface? Like say for example, if you are considering that on this piece of plain surface, you just prick some needles of different heights. Let us say that here you prick a needle of long height, here you prick a needle of lower height, again here you prick a needle of higher height, like that you prick needles all over this of different heights. Does it constitute a surface? No. If it has to look like a surface, what do? We interpolate that surface. Okay. So, the job of the training phase is to interpolate that surface. Why? Because if your surface is interpolated, in that case only when we are feeding a test pattern, okay, we come anywhere to this bed and we want to determine that what is the corresponding real value output, what is the corresponding output value, then we simply look at the interpolated surface that we have got and determine its value. So, now this interpolation, so this gamma, so about the gamma we can say two things, that the training phase constitutes the optimization of the fitting procedure. So, there is a training phase which constitutes the optimization of the fitting procedure. Now, the optimization is very important because you know, while feeding the training data, I think I have discussed this a few times earlier also, that in our training set itself, in our training data itself, there could be some noisy points. Okay. So, during the fitting, if there is some abnormal noisy points, like say for example, we have got a fixed set of surface like this, but suddenly we find that okay, there is some point, okay, which is lying very high, okay, then that is simply a point in error. So, when we draw the surface, we should not include that point. So, there is going to be some optimization of the fitting procedure. So, only through optimization we will be able to get a surface. So, procedures for the surface gamma is the one that we are going to fit, okay, and this fitting is obviously based on known data points. And then the second thing is that in the generalization phase, okay, the generalization phase can be looked upon as an interpolation between the data points performed over a constraint surface. Why are we calling that as a constraint surface? Because we are feeding the known data points. Now, feeding the known data points means that your surface has to always pass through these known data points. So, it is becoming a constraint surface. So, in the generalization phase, it is the interpolation between the data points, interpolation over a constraint surface. Okay. So, do not look at it from the usual characteristics way, like drawing the neurons, feeding the synaptic links, and then computing this summation of W1 x1. Now, just a rethinking, RBF means that it is a rethinking where you are now thinking in terms of the whole problem to be an M0 dimensional space to 1 dimensional space of mapping problem, and where the given points are constituting the constraints to the surface that you are going to feed. Okay. Is that clear? Now, that basically results in a multi-dimensional interpolation, okay, multivariable interpolation. So, we are considering multivariable interpolation, sorry. So, we have got a set of n different points, which constitutes this set. So, xi, the set of xi which belongs to the M0 dimensional space, because M0 is the dimensionality of the inputs, and we get and we also take a corresponding set of n real numbers. So, what happens? We take the set of the corresponding set of di's. So, we are feeding x1 vector, xi vector, and correspondingly the output is di, which is a real number. In fact, because we are taking only a single neuron as the output, the output that we are getting is in 1 dimensional space. So, it is R1. So, di belongs to the R1 space, and of course, here for both these things we have to know that our I could be 1, 2, etc. up to n, and the multivariable interpolation problem is that to find a function. So, the problem is to find a function f, and what is the f? F should be a function that we are getting n such these things, right. So, n such patterns are being fed. So, there are n number of points in this M0 dimensional space. So, it is a mapping from this n dimensional real space to 1 dimensional real space that satisfies what? That satisfies which ones? All the training points, that means to say that all the constraint points should be satisfied. So, we have to find a function like this such that, or fulfilling the constraint that at the point xi we must be having what? F xi is equal to di. Yes. Why hesitate to tell? Because it is after all a mapping from the xi to di. So, the function, so it is di is equal to f xi simply, and we do not know that what that function is. That function is nothing but the interpolating function, correct. Okay. So, it is to satisfy f xi is equal to di for I is equal to 1, 2, etc. up to n. And now look at the radial basis function. Now, in radial basis function, what we are doing? We are taking the phi functions for mapping from the input to the phi space, and then all the phi outputs we are linearly combining together in order to get the final output. So, we can express, I mean, from a radial basis function network. So, using RBF, okay, we can obtain the same function fx as fx is equal to summation of wi times phi, and we can say that phi whose argument is x minus xi. That means to say that we are taking different phi functions, okay, which are centered around the different xi's, okay, followed. So, we are having the inputs as x1, x2, x3, x4 like that. So, we are considering various such phi functions, okay, which are centered around all this, and we are having in fact n such phi functions, and we are going to add up this, that that all these linear all these outputs will be linearly combined. So, we have got n such synaptic weights will be there. Synaptic weights will be from the output to the from the hidden to the output, okay. So, there will be n such, and we will be actually mapping from I is equal from the hidden space of n dimension to the output which is of 1 dimension. So, in this what is it that where the phi functions that we are having. So, the phi with argument x minus xi, okay, given that I is equal to 1, 2 up to n, okay, is a set of n arbitrary functions, is a set of n arbitrary functions. And what are these functions known as? Set of n arbitrary functions known as radial basis functions. So, this is the way our function is defined. Now, if we have to use the radial basis function for interpolation, then what we have to impart upon it, that this equation that we have got should be satisfied by this equation, because this equation is acting as a constraint to the surface interpolation that we are making. So, these constraints should be put into this equation, meaning what? If we are taking the first pattern, let us say, if we are taking the x1 as the input to it, then if we have fx1, fx1 should be equal to d1, okay. So, d1 should be equal to what? Summation of wi phi of x, instead of x we will be making it as x1, x1 minus xi, and we have to compute all these n different outputs. So, for x1 pattern we will be getting n different outputs coming out of the n different radial basis functions that we have constituted, okay. Now, what you do is that you take I is equal to 2, so that I mean next time you are importing fx2 is equal to d2, now you substitute d2 over here, even d2 also will be expressed as a weighted summation of all these n different radial basis functions, okay. So, each point will be expressed as a summation of all these radial basis functions, and then we can now write, I mean after putting these constraints, after applying these constraints, it is possible for us to write this equation, okay, reformulating this equation in a matrix form. How? Just look at it. It can be written as a matrix, a phi matrix, which I am going to define shortly, where, okay, let us write down first phi 1 1, phi 1 2 up to phi 1 n, then phi 2 1, phi 2 2 up to phi 2 n, and going all the way up to phi n1, phi n2 up to phi nn. Okay. This times W1, W2 up to Wn, and this results in D1, D2 up to Dn. Very simple to verify. What is D1? D1 is W1 phi 11 plus W2 phi 12 plus etc. up to Wn phi 1n. D2 is W1 phi 21 plus W2 phi 22 up to W2 up to Wn phi 2n. Okay. Dn will be likewise. So, here the definition is that phi ji that we are considering is the phi whose argument is xj minus xi. Okay. Norm of this. So, here what is this xj? Xj is the point for which you are calculating this function, right. Okay. So, I think I mean, because the time is ending today, and a long time back I was shown with that sign 5, okay. I have to stop. So, here I mean, this is a formulation that we have got in terms of the I mean, after putting the constraints of the radial basis function, and then we will be discussing more on this in the coming class. Thank you.